I'd like to thank everyone for joining us today. Welcome to today's CNCF webinar, Getting Started with Container Runtime Security using Falco. I'm Jerry Fallon. I'll be moderating today's webinar. We'd like to welcome our presenter today, Loris Degioanni, CTO and Founder at Sysdig.
Thank you very much, and welcome everyone to this webinar. Today we're going to talk about runtime security, and in particular runtime security with an open source tool, which is also a CNCF incubating project, which is called Falco. My name is Loris Degioanni. I'm CTO and founder of Sysdig. Sysdig is my second company. My first company was called Case Technologies and was the commercial entity behind an open source network analyzer called Wireshark. So I have done open source for my whole career in the networking space first, and now in cloud native. Right now I work for a company called Sysdig. Sysdig offers visibility, observability, and security tools for cloud native, Kubernetes based, and cloud and container based applications. Sysdig is based heavily on open source, but offers also commercial solutions on top of our open source projects like Falco. We're heavily integrated with the rest of the ecosystem, and we tend to focus on enterprise customers, and we have essentially products that scale and offer solutions to any scale when it's a matter of security and visibility for Kubernetes. Today we're going to talk about an overview of runtime security, comparing different approaches when dealing with instrumentation for runtime security, and understanding essentially the pros and cons of instrumenting your containers, your applications, your workloads with these different approaches. We're then going to dive into Falco. I will give an overview of Falco, and then I will try to become a little bit more practical to show, a little bit of the Falco architecture, how rules work, and so on. And then we'll try to put this in practice quickly in terms of showing Falco in action and seeing it essentially in a demo. And then I will finish the presentation. I will finish the webinar with a little bit of history and what's coming next, for Falco. So first of all, overview of runtime security. Let's start by what is runtime security and why we need it. So runtime security means being able to observe and protect your software, your containers, your applications as they run. They run in development or test environments, or they run, even more importantly, in production. This is extremely important because security breaches and risks happen while our software is running. So it's very important to protect the software during the whole, CI/CD pipeline. But in practice, the risks happen while our software is actually deployed somewhere and runs, right? Example of stuff that you can accomplish with runtime security: detecting malicious behavior, understanding if an image has drifted from when we created it and we put it in a repository. Find issues or vulnerabilities that are only present and only surface during the runtime of your containers. Detecting threats that are like zero-day vulnerabilities that were not yet exposed and documented when your software was created and was pushed to a repository. Runtime security is an integral starting point for things like incident response or forensics. Typically, your forensics activity, understanding the blast radius of an attack or something like that, always starts essentially from signals and data that are collected during runtime. And of course, runtime is also extremely important in terms of compliance, because frameworks like PCI, NIST, or SOC essentially depend very much on understanding what's happening while your containers, your applications are running. This slide depicts a little bit sort of the CI/CD journey, right? And I used to articulate these as build, run, respond. The phases of life, the stages of life of a modern application. And as we know very well, security in cloud native is not only one of these items, but it's making sure that the whole journey of your code from your laptop to a production environment, and after production, after maybe the containers are gone, is all properly monitored and secure. During the build phase, it's important, for example, to have vulnerability scanning, configuration validation during runtime, as we were saying, runtime security, vulnerability reporting, security monitoring. And then, of course, you need to respond to the issues that happen. So incident response, forensics, audit. It's important to clarify that all of these are essential when talking about the correct posture for cloud native applications. This webinar focuses specifically on the middle of the slide, on the green part, not because we think it's the only important one, or not because we think that Falco is the only thing that you need to deploy, but because we think that Falco is an important piece in the equation. So as you think about this, as you think about your holistic approach to this webinar will hopefully, give you information about how to cover the central piece, and in particular, how to do that with the cloud native CNCF tool, which is Falco. Let's go a little bit more into the technology here and into the actual implementation. And let's start talking first of all about where runtime security starts. Runtime security starts from being able to collect the best data from processes and containers that are running live on your infrastructure. So if we simplify the concept as much as possible, we have, for example, something like an application that is running inside the container, that is running on top of an operating system in a machine. And of course, you will have almost guaranteed, multiple applications and multiple processes running on top of multiple containers, running on top of multiple machines. So this is just a little piece of the equation. But from this point of view, essentially, it's very important to collect signals that are very rich for this application. And in order to do that, essentially, we need to be able to intercept the path of communication between the application and the external world. And this goes through the operating system, right? And we want to understand what this application does on the network, for example. We want to understand what this application does on the file system. We want to understand what this application does in terms of activity, like executing commands, spawning processes, doing inter-process communication, accessing data, all of this kind of stuff. And typically, all of this information goes through the operating system. And so we want to be able to intercept it. One way to do that is a technique so-called LD preload. LD preload consists in taking a running application and somehow replacing the libraries that this application uses to talk to the operating system. So we, instead of using the normal, for example, C libraries, the C library is what is typically used by the majority of the applications to access the file system, doing everything that has to do with system calls, like opening files, establishing connections, all this kind of stuff. We can somehow, as the container loads, replace the libc that is inside the container by maybe mapping a volume or something like that, and then use an environment variable to tell the container, okay, go and use this different libc, which is instrumented. The instrumented libc is able essentially to act as a pass-through for all of these calls that the application does to the operating system, and collect them and ship them somewhere so that they can be analyzed and can be used as signals for runtime security. LD preload is used by many projects and vendors because it has the benefit that it works pretty much everywhere. It's efficient, and it's a relatively easy and relatively low risk way to essentially observe anything at high granularity that your applications are doing. It also has limitations. The big one is probably the third one here on this slide, which is in order for you to be able to replace libc, your application needs to use libc, which is sort of traditionally a good assumption, because everything, C applications, Java applications, Python, you name it, they all use libc. But there are nowadays whole classes of applications that don't. For example, Go as a programming language, very interestingly, really implements its own runtime. And one of the design kind of architectural choices of Go is that Go produces fully static binaries. So Go doesn't use external libraries. So this trick of loading different libraries doesn't work for a Go application, which, as you can imagine, is a pretty strong limitation in cloud native. And of course, LD preload requires you to go and instrument every container. So let's look at another way to do this. Another way is by using ptrace. Ptrace is a functionality in the Linux operating system, and it's actually the facility in Linux that is used to create stuff like debuggers. So GDB is essentially a glorified user interface on top of ptrace. I don't want to diminish what GDB does. It's something that all of us use all the time. But the magic to freeze a target process, set a breakpoint, introspect the process, the registers, the memory, change stuff into the target process. This is all stuff that GDB essentially just calls this Linux system call called ptrace to do that. Ptrace is nice because it is a facility of the operating system, so it's much more accurate. For example, when you use ptrace, you don't need a dynamic library to do the instrumentation. So these covers, for example, Go processes. Ptrace is language and stack independent because it relies on Linux, on the operating system, and not on a library or on a piece of functionality or on a language that you're using. It's also safer than LD preload because it doesn't require you to do the relatively dirty trick of replacing libraries, but you can do that by just telling ptrace, okay, I want essentially to introspect every single system call. So beautiful. Only problem is ptrace is very inefficient because if you look at the diagram, every time there's essentially a request like opening a file or establishing a connection, you need to do a bunch of stuff essentially in the operating system to pass all of this data to a separate process, which is depicted as an agent here in the diagram, to that can receive this data. So ptrace is the magic bullet for everything, with the only problem that it's too slow typically to be used in production. And of course, with ptrace as well, we are required to instrument every container. let's look at another possible way to do this, which is kernel-based instrumentation. So what we do here is slightly different. Here we have still a diagram of the machine, and we see 3 containers on this machine based on 3 different essentially container runtimes. And what happens here is you deploy essentially your instrumentation as another container running on the same machine. This container, what it does is it instruments the operating system. Linux nowadays offers a functionality called eBPF. eBPF is the acronym for Extended Berkeley Packet Filter. And it's essentially a full-blown, powerful virtual machine that can be used to execute programs inside the kernel of the operating system. eBPF is cool because essentially it allows you to add functionality to the kernel of the operating system, but in a way that is fully validated and that guarantees that you are not crashing the operating systems or generating deadlocks in the operating system. By doing this, it's possible essentially to create a layer of instrumentation that now sits underneath the containers. So you don't need to live inside the containers, and that is able to, without any change, without any sidecar or installing anything in the container, it's able to collect the data that is required. Kernel instrumentation has the advantage of being extremely accurate because it runs in the kernel of the operating system. You cannot fool it. It's extremely efficient and extremely scalable. Extremely efficient because the data is collected in a way just really where it's generated in the kernel of the operating system, and it's scalable because you don't need, it's the only way where you don't need to put something inside every container, but another container, an external container can do that. So imagine having, I don't know, 100 containers running on a single machine with LD preload and with ptrace. You will need to instrument 100 different things. With kernel level instrumentation, you will only need to do the instrumentation once. When talking about instrumentation, the other thing that is important is metadata collection and applying metadata to the detections. So this slide shows a bunch of hosts, each of which is running 4 containers. And here the color coding is essentially the service that these containers belong to. When working with anything related to runtime security, you typically don't want to approach things like on the left side of the slide, but you want to look at things like on the right side. So service by service, you want to apply rules that are per namespace, per service, per deployment, and not per host or per container. All right, this is the theory. Okay, now let's move into the practice and let's start talking about Falco. What is Falco, first of all? Falco is a runtime security engine based on observability from the kernel. So when I was showing you the different options before, the one that Falco privileges when possible is collection based on access to the kernel of the operating system because of the reasons that I was mentioning before. Sometimes this is not possible, and I will show it to you quickly in the demo. In that case, we switch to other mechanisms like ptrace, but by default, Falco wants to be as scalable and efficient as possible. So when BPF is available, that's what we use. Falco is designed to be consumable and modular. So as I was saying, Falco is designed not to be your complete solution for Kubernetes security, for cloud native security, but is designed to be a component in it that can be orchestrated and can be composed together with other stuff to create the full solution that is ideal for you. And this full solution, of course, can be part of something that is built completely out of community built and maintained pieces. But Falco is also designed to potentially, if required, to be connected to proprietary components and to commercial products. Falco puts a lot of emphasis not only on using the kernel as a source of truth, but also on enriching the data with metadata so that your approach can be service-oriented. It essentially allows you to create or to leverage a bunch of rules, and then it gives you alarms when one of these rules is violated. Falco is a CNCF incubating project. We released Falco in 2016. It became part of CNCF in 2018, and it was promoted to incubation in 2019. We are strongly driven as a community by community principles. In particular, we are inspired by everything that is cloud native and Kubernetes first in the way we manage our community. We really try to be, like the voice of our end users and work together with them. But we also want to be vendor friendly and vendor neutral. So as you can see, there are multiple commercial entities that take Falco and enhance it and base their products on top of Falco. A couple of examples of using Falco in production. One is Shopify, big production environment. It's essentially a PCI compliant environment in the cloud in AWS/EKS. And this is, Shopify is a big company that does a lot of transactions, and they are, $100 to $250 million of transactions per day are essentially in an environment that is protected by Falco, and where Falco contributes to establishing essentially PCI compliance and making the environment PCI compliant. Shopify specifically, I recommend to go to the CNCF YouTube channel. There was a wonderful keynote at the last KubeCon in Europe, in Amsterdam, where the Shopify team, together with Chris Nova, showed essentially on stage Falco used by Shopify, and it's very interesting if you want to learn more about their use case. Another use case is Skyscanner. Skyscanner has 200 plus nodes on 30 clusters with 160 services on top of them. And I have a link to the blog post in which they describe essentially how they use Falco and the kind of evaluation that they did with Falco before putting it into production. For example, it's very interesting to look how important for them the overhead of this instrumentation was. And we go back to, ptrace versus kernel module and so on, and how they really scrutinized, Falco performance-wise and overhead-wise before deploying it on their infrastructure. And blog posts like that are cool for me to see, because of course the Falco community and the Falco engineers put a lot of effort into making it efficient. So seeing how it can be used in production is always very, very rewarding. Architecturally, Falco is relatively simple. It has inputs, an engine, and outputs. Inputs are all of these events coming from instrumenting the application, so system calls, kernel events, activity events, user activity, network data, all of this kind of stuff, and also Kubernetes events in the form of audit events and in the form of metadata. All of this goes into the engine, which receives rules as its other input, and essentially the rules are matched against the stream of data that is constantly coming into the engine. And if rules match, an alert is generated through a number of ways. Again, Falco is designed to be composable. So gRPC, webhooks, syslog, SDK, Slack, you name it, We have all of these ways essentially to notify you that some rule was violated. Collection-wise, two great sources of data, as I was saying. One is the system calls. The other one is the Kubernetes events, and rules can be created on both and can be mixed and matched. So you can mix a rule that is specific on, for example, of a system call, like opening a specific file, which is based on a Kubernetes action, like, I don't know, spinning up a service or something like that. And rules essentially can take these two sources of data and alert on either one or both together. Rules. So what's a rule exactly? Compared to other tools, like, for example, I don't know, an OPA, to mention something that is a very popular rule engine for Kubernetes, Falco focuses more on staying close to the edge, high performance, and simplicity. So when OPA optimizes a little bit more for high level overview on the cluster and high expressiveness, Falco focuses more on being everywhere, seeing stuff everywhere very, very efficiently with low overhead, and rules that are simpler to craft, essentially. Some examples. A share is running a container. The rule is container ID different from host and process name equal bash. Override system binaries. There needs to be access on a file descriptor in a directory, and this directory can be, one of the directories that are in this rule. So as you can see, it's essentially Boolean expressions that can be used to chain checks that are done on different different fields, and the list of fields is pretty big, and it's essentially documented in the Falco GitHub. Example of, for example, spawn a shell, a database spawns a shell. This is the condition, process name in database binaries, and process is spawned, and the process name is not one of the processes that you would expect. There's an output, which is what you see when you receive a notification when this rule is violated. The source, as we were saying, it can be Kubernetes or system call, description, and priority and text. Rules can contain lists and macros, so that can be written in a more compact and reusable way. And of course, we don't expect you to, download Falco and have to write your own rules and learn the syntax and so on. Of course, you're welcome to do that, and we try to document as well as possible. But Falco comes packaged with tens and tens and tens, probably hundreds at this point, of rules that are pre-packaged for you by an active community of people that maintains these rules, keeps an eye on the noisiness, adds constantly new applications and new tools and stuff like that. The rules are even, aggregated and tagged based on the different uses. For example, there's a MITRE rule matrix where rules are tagged, and you have a subset of rules that is just for MITRE framework, and you can use those, exclusively with Falco if you want to essentially be compliant with that framework. All right, let's start with the slides for a second, and let's actually take a look. So let me actually go into my virtual machine, and let me just run Falco. Right now, this is the possible way to run Falco and give it a try. You download the tarball from the Falco repository, and then you just run it. And when you do that, nothing happens, but I can start operating on this machine, and say I can generate some pseudo malicious activity, like let's modify a binary file, which is something that is never that nice. And immediately, as you can see, Falco is just under the hood here in this machine, and looking at what's happening, and it detects this and tells me essentially file below a binary directory open for writing. It tells me, information about the user, information about the process that that was the target for this, the command line that generated this, the process that was the target for this, who was the parent, all of this kind of nice information that right now I just get on standard output, which is one of the many ways Falco ships out its output, but it can be, anything else that we want. Let me try to do, actually, to start a container. So I'm just starting a Ubuntu container. And when I do this, immediately Falco tells me, okay, somebody spawned a shell in a container, which is normal here because it's an Ubuntu container, but you would agree with me that in production, it's never good when somebody just spawns a shell in a container that is supposed to be immutable. So Falco gives me a notice for that, okay, careful because there's a container now and somebody that has a root shell essentially inside the container. And again, inside the container, I can generate some malicious activity like garbage into /dev/fake device, for example. So I simulated creating essentially a file under dev, and Falco essentially tells me that a program that it doesn't trust has done that. So as you can see now, I'm inside the container, but Falco, even if it's running in the host, is able to essentially keep track of what's happening inside this specific container and any other container, and doesn't matter how many I have running on this machine because it uses it installed, this little eBPF thing in the kernel of the operating system and now sees everything. At the same time, with maximum efficiency and by barely slowing down the target, the target processes. Of course, I can also run Falco on this machine as a Docker container. So now Falco, just started inside a container. This is an even simpler way to run Falco, but notice how I can, again, generate malicious activity anywhere in the machine, and even if it's living in a container, Falco is still able to see for its container, the host, and any other container. So the beauty of this is that, at the point deploying something like this, especially orchestrating the deployment of something like this, becomes very nice. You don't need to have sidecars. You don't need to have to link libraries. You don't need to use all of these more invasive ways to deploy it. You just use a daemon set on Kubernetes and you tell Kubernetes, I would like to have one of these running on each of my physical hosts. And then, with a little bit of glue configuration to tell essentially Falco where to pipe these events, you're good, you're covered, right? So that's the power and the richness of Falco. Similarly, if we want to look at these, actually, let me go out to full screen. Here, I have actually a more like realistic deployment of Falco, where Falco is running on AWS, in this case, on a Fargate task. So here, I have my task, and I can take the IP address of one of the containers on my task, and I can go and log into it. Oh, looks like I lost my connectivity. Is that the right address? No. There it is. And then go inside, and I can do the same. I can just simulate /bin/cat, the same thing that I did before. So now I logged into the container, and I simulated activity, and now I can go and look at the logs in CloudWatch, and as you can see, I'm getting the logs of Falco essentially detecting this. In particular, notice how here specifically, Falco was run in a Fargate task. So in this specific instance, we don't use the kernel module to instrument because it's not possible in Fargate, and we revert to a technology which is called pdig, which allows Falco essentially to collect this information by sitting inside the container and using ptrace. So as you can see, from one point of view, Falco tries to be as efficient as possible by defaulting to like eBPF and kernel module, which are the most efficient ways when possible. But when not possible, it can also go into like orchestrated container technologies in the cloud like Fargate, and still work by using other technologies like ptrace to do the instrumentation. So there's quite a bit of sophisticated stuff going on under the hood here. Okay, just another couple of slides before we go into questions. So first of all, a little bit of history. We actually started Falco in 2016 as a way to apply some of the concepts in network security to broader containers / cloud native security. As I was mentioning at the beginning of the presentation, my background is packet capture and in particular Wireshark. And another very important class of things that you can do with packets is network intrusion detection. Tools like Snort or Suricata and so on essentially are based on capturing network packets, applying rules on top of the network packets, and giving you alerts if something, for example, is sending you malware or something like that. And of course, doing stuff from the network point of view, doing this kind of stuff from the network point of view is harder and harder, in a world where we have heavy orchestration, heavy encryption in the network, and the use of containers that make everything opaque. So Falco was designed with a similar concept, but with a different vintage point, the system calls, the runtime data coming from the operating system, which is much closer to the final application, and it's much more collectible in cloud native. Falco evolved quite a lot, both in terms of becoming part of the CNCF and in terms of features, and grew quite a bit in terms of contributors and number of users. Among the things that we added recently to Falco, like in the last 6 months, many rules improvements, and in particular, groups of rules for like pod security policies, for MITRE framework, for crypto mining, which is another one that is pretty popular with our users. We added a gRPC input and output interface. This goes toward making Falco able to integrate well with any other tool in the ecosystem, and also being composable and being essentially a part of the stack that you can use in different ways. Based on this general input-output interface, we create a lot of integrations, Prometheus, Slack, Elasticsearch, AWS Lambda, and so on. We also worked quite a bit on deployment of Falco, trying to make it easier and easier, for example, by offering Helm charts that come essentially prepackaged as recipes. And also, we've been spending quite a bit of time recently on ptrace instrumentation to make it possible to collect data for stuff like a Lambda, exactly like I showed you before during the demo. There's a blog post that we released recently with stuff that we added recently. I encourage you to go take a look if you want to learn more. Roadmap wise, what we are looking into as Falco developers, first of all, the most important thing that we put on top of everything else is expand our community by delighting our users. So we are focused here on building something that solves a problem in a way that is not only effective, but also elegant and cool, actually, and nice to use. Lowering the barrier, of course, Falco is and will remain a distributed tool that needs to run everywhere if you really want true security in potentially big and complex infrastructure. So we are always talking to users that struggle with ease of deployment, with maybe performance in particular situations, or maybe with stability. So the team is really focused on trying to just making this experience better and better so that Falco can be used more confidently by people. Integrations and being able to plug Falco into many different things, cloud things, Kubernetes things, and so on. And platform coverage. Fargate that I was mentioning before is an example, but for sure, with something that collects the data in such a rich way, and that is really based on the idea of having the best data, coverage, and I don't know, Fargate, Lambda, Cloud Run, all of this kind of stuff is always a focus and the direction for us, so that Falco can really be used broadly and cover any possible use case. And we are at 45, so I'm going to just put some links on the screen, and I'm going to stop here to see if there are questions from the audience.
Okay, well, thank you very much for a wonderful presentation. As I said before, feel free to drop some questions into the Q&A section. Looks like we already have one here from Rajesh that says, when is the GA version due?
Falco has been GA for quite a bit now. So if you go to falco.org and you follow the instructions, you can install it on your cluster, and Falco is a tool that can be used for production-ready workloads. So GA-wise, I would assume, we're always releasing new stuff, but Falco should be considered, ready to be used.
Okay. Does anyone else have any questions at all? Okay, Yuri Lee says that he installed Falco and has an error that repeats. Falco internal syscall event drop, one system calls dropped in the last second.
Okay, this is a pretty benign error. I recommend you just go to our GitHub here and open an issue, and some of the engineers that work on Falco will be able to help you. But it looks like you have some kind of drops, so it could be a configuration of Falco. But if it's just one system call that is dropped, it's probably like just physiological. But it's something that we see from users once in a while, and we'll be able to help you with that if you just go to our GitHub and you open an issue with us.
Okay. Does Sysdig provide any support for it if necessary?
Sysdig does provide support for Falco, yes. Sysdig also offers a product called Sysdig Secure that is heavily based on Falco for runtime security. So Sysdig Secure also offers a bunch of other functionality like image scanning, forensics, audit stream, compliance, and all of this kind of stuff. But for, let's say, commercial use, you can come to Sysdig for both essentially support with running Falco as an independent tool, or for commercial tools that are based on top of Falco.
What is the difference between Falco and istio?
So istio is more like, let's say, a generic network mesh. So istio is a mesh, a network of sidecars that you put, of little proxies that you deploy as sidecars inside all of your pods, near your containers, near your applications. And essentially with istio, all of the network traffic of your applications, of your containers in Kubernetes will go through the istio proxies. At that point, istio can do a bunch of stuff that ranges from observability, circuit breaker and testing, and also security enforcement and microsegmentation. So istio is very much network oriented, and it's another important part of the runtime security equation, and operates especially from the security point of view at the network segmentation level. While Falco is more like able to see inside the containers and to notify you when something that you should pay attention to happens inside your containers. If we go back to the previous world, the previous data center world, istio is more like your firewall, your checkpoint firewall. Falco is more like your intrusion detection system, like your SourceFire / Cisco intrusion detection system. You want both because one essentially is your lock on the door. The other one is your security camera. Falco is the security camera. Istio is more like, among other things, the lock on the door.
Can you elaborate on the compliance rules supported by Falco OOB?
Yes. So compliance is many things, right? And starts at the CI/CD level. Starts in the build phase of CI/CD, where you want to check configuration for your images and so on. But then compliance is also runtime, and essentially making sure that actions that are a concern from the security point of view are not performed at runtime, and if they are, you are notified, and there's a trail that essentially allows you to document them and improve essentially the compliance of your infrastructure. Examples of things that you want to check at runtime from the compliance point of view: not running privileged containers is a good example. Specific policies on the data that you have, or on the processes that you run. Not running, as I was showing before, shells in your production environment. All of this kind of stuff can be detected by Falco, and Falco can report all of these information and allow you essentially to create a paper trail of anything that happened in your environment across time, so that if an auditor comes, you can show that in the last 6 months you didn't have any privileged container that was executed in your infrastructure. Falco has a set of rules that are particularly and specifically crafted to match against the main compliance frameworks, for example, PCI. So if you go to the Falco rule set, which is a big YAML file, and you look at the tags, you will see that many rules in the Falco rule set are tagged as PCI. These are rules that have been created by security professionals, by members of the Falco community, that will notify you if something that happens on your infrastructure violates a specific PCI rule, a specific PCI entry. And when you deploy Falco, you can essentially, if you want, choose to only deploy rule sets that map to specific compliance frameworks and offer a certain percentage of coverage for these frameworks.
Can Falco be integrated with Cilium?
Not really, because they do different things. The thing that Falco and Cilium have in common is that they're both based on eBPF. So they both use these powerful and revolutionary functionality in the Linux kernel. But Cilium uses eBPF to be much more attached to the networking stack, while Falco wants to be, again, a broader intrusion detection system. So Cilium, from the point of view of essentially integration and being used together, is a little bit more like something that matches Istio rather than Falco. So some similar technological choices, but we don't really have deep integration among the tools.
Okay, does anybody else have any questions at all? Do you have any planned integration with notifications beyond Slack?
Yeah, there's a bunch. I mean, again, go to the website. I cannot list all of them here. But if you need to integrate Falco with something, very good chance it's already there. Slack was an example, but there's you name it, log collection systems like Splunk and so on, stuff like PagerDuty and similar, chats, webhooks, monitoring tool Prometheus. So there's a bunch of them. So it's not only Slack.
Is there any UI on top of Falco?
Not on top of Falco. Open source. You can buy Sysdig Secure. It's commercial, but it gives you a very, very nice UI on top of Falco.
Is there a difference between system Falco service and Falco in container?
No. If properly configured, no. Because they do the same thing. So we give you the choice from running it in the system, for example, installing it in the host as a tarball, or running it inside a container. Functionality-wise, performance-wise, they are absolutely equivalent. So whatever works best for you.
Do we have any more questions? We have about 3 minutes left. Talking about performance, what is the overhead?
Okay. Market the answer, it's low. In practice, the overhead depends on the workload profile of the system that Falco is observing. So if Falco is properly configured and tuned, and the system is not like an edge case, you should expect to see something like a handful of CPU percentage points used by Falco, and an amount of memory that varies depending on what you do with Falco. Because if Falco is configured to only look at local data and not consume the Kubernetes state, then the memory footprint is tiny. If Falco is configured to fetch the Kubernetes metadata because you have service-oriented rules or stuff like that, then there's a memory requirement in terms of bringing in essentially the Kubernetes state to understand metadata and all that kind of stuff. And memory can grow higher to up to, let's say, hundreds of megabytes or something like that. So that depends. But overall, again, Falco has been designed to run in a production environment in a way that whose overhead should be barely measurable.
Well, thank you very much. That's about all the time we have for today. Have a wonderful rest of your day.